Answer is that f, or if you want, you can say f of x, y, is this right here, right? This right here, but instead of that, a constant. And I'm going to go ahead and kill these x's off now. So it should be x squared y plus x ln x plus any constant. There we go. How many potential functions are there? I said find its potential function. There are an infinite number of them, but they're all within a constant of one another. Now, if you're not quite sure what we just did, I ask you now to take the gradient of this. Take the gradient. So what is the partial of this with respect to x? 2xy, and then you'd have to differentiate that. And if you differentiate that, product rule, you get natural log x. And then, well, natural log x plus 1. Right? So, differentiate this with respect to y. What do you get? X squared. Okay? Let's go back up to this one. The one before that we did, right? I asked you if that was conservative or not, and you said yes, right? Could we now find its potential function? Yeah. Would y'all like to? Sure. Do it real quick. So this is conservative, yes, because we already checked it. Now what we're going to do is we're going to find its potential function, or the infinite number of them. So what do I know? I know that the gradient of f is equal to the partial of f with respect to x, partial of f with respect to y. But for us, that is 3 plus 2xy, comma, x squared minus 3y squared. Which means that partial of f with respect to x has to be that, right? Let's start with that. You could also start with the other one if you wanted to. Partial of f with respect to y is the other one. But I'm going to just start here. So I know that the partial of f with respect to x must be 3 plus 2xy. I'm going to integrate both sides with respect to x to undo the partial. And that gives me f on the left. On the right, 3x plus x squared y is the antiderivative of this with respect to x. Plus, same story. It's some function of y that I don't know, right? Some function of y that I don't know. And then I take the derivative of this with respect to y. And derivative of this with respect to y is? Yeah, just with respect to y. We just get what? X squared plus partial g with respect to y, or g prime of y if you want. Okay, but what do we know this has to be equal to? What does that have to be equal for this to work? This must equal this, right? So that means that x squared plus the partial g with respect to y must equal x squared minus 3y squared. And that's just an equation, right? So let's solve. X squareds go away. You get partial of g with respect to y must be negative 3y squared. So remember, we want to know what g of y was, right? So to get g of y, we're going to just do the antiderivative on both sides with respect to y. Right? You could kind of even look at that and tell what it is, but I'm going to keep going. So now this, I take the antiderivative of the partial of g with respect to y equals the antiderivative of negative 3y squared with respect to y. This is just g of y, right, or g? And then this is negative y cubed plus some constant potentially, right? And now I can plug that in right here. And I've got my answer. So my potential function, or you could say family of potential functions, would be this. F equals 3x plus x squared y, what? Minus y cubed plus any constant, right? So if I'm just looking for one potential function, you could just let your constant be 0. And then there's a potential function. Should we check? Yeah, let's check. What's the partial of this with respect to x? 3 plus 2xy. What's the partial of this with respect to y? X squared minus 3y squared. See? We have created the scalar function that when you take its gradient, you get that field. Your field must be conservative for this to work. If it's non-conservative, then you're not guaranteed that there's any, well, then there's no potential function. Did you hear what I said? If your field is not conservative, there is no potential function. If it's conservative, there is, but if it's not conservative, then there's not going to be a potential function. This is kind of putting several ideas together into this problem. So imagine you're sitting there, you're taking a test, right? And you get this problem. If f is this field, find f dr. The curve C is given by that vector equation or vector function. So you could do this like we started class, right? We started class, you just go grind out the integral, okay? Or you can start asking yourself some questions like, is this conservative? Is that a conservative vector field? Now, is it? It is conservative. That's the same field we just did, right? So I notice here that f is conservative. Right? F is conservative, which means that there's a little scalar function, right? And I can go find it. Now, we did that as well, didn't we? What was the scalar function? I'm going to write f as f of xy, just so you can see different notation. We did it. What was it? Didn't we do this? Wasn't it x squared plus x squared y x ln x plus c? Let's use c as 0. Is that all right? Okay, so there's the potential function, right? So this right here is the potential or a potential function. Why is this useful? I can use the fundamental theorem of line integrals, and to figure out what that integral is, all I need to do is evaluate that scalar function at the two endpoints of the curve that they gave me, right? I don't have to do any integration at all. Now, I had to do a little integration to get this, though, right? I will admit, we did have to do some work. So using the fundamental theorem of line integrals, what I know is that that integral up there is equal to the line integral over c of the gradient of some f dot dr. But I know that that's going to be that f evaluated at the two endpoints of the curve. Subtract, right? Subtract those two. Okay? The key to the whole thing is the fact that the field they gave me is conservative. It's the gradient of some f, and I was able to find that little f. Once I find that little f, I can use this. Now, do we know our two endpoints? Let's get them up here. So r of, let's do r of a first. What's r of a? That's r of 1. What do you get when you plug 1 in? 2, 2. Okay, and when you plug in b, b is the other endpoint. B is 2. Oh, it's 2, 3 up here? 2, 3. And then this one is what? 5, 4? Okay, 2, 3, 2, 3, 5, 4. So what I now need is to take my scalar function and plug in the vector 5, 4. and then my scalar function and plug in the vector 2, 3. Evaluate, and I'll be done. Okay, what happens when you plug 5, 4 into this? Well, it's not going to be pretty, but okay, when we plug in 5 for x and 4 for y, we get 5 squared, 25 times 4, 100, plus, and now 5 natural log 5, 5 ln 5. All right, that's what I get when I plug in this. Minus, now plug in 2 for x and 3 for y. So 2 for x, I get 4 times 3, 12. I have to subtract the whole thing, right, because it's minus whatever this is. Plus, and now plug in 2. So 2 ln 2. And that's just some number, right? And we've got it. We've got our answer. Now I'd like to show you what would have happened had you not used this. I want you to see what you would have faced, all right? If you don't use this whole idea, then what you would have been stuck with is trying to do this. The line integral from a to b of f, the field evaluated along the curve, whatever that is, dotted with the derivative of the curve dt. That's what you would have had to have done. That's what we started class with. And so let's see here. I want to go real fast here because I'm just trying to make a point. My integral would have to go from 1 to 2. Then I would have to take this field and evaluate it along this curve. So everywhere I see x, I do this. Everywhere I see y, I do this. Let me do that. So it'll be 1 plus 2 times x, t squared plus 1, times y, t plus 2. Okay, and then plus natural log of t squared plus 1. Okay, that's me doing just this, right? The field here evaluated along here. Now I need comma, then x squared, which would be t squared plus 1, that quantity squared. That's my field evaluated along the curve. I then have to dot that with the derivative of my position or my curve, which would be 2t 1 dt. And then you dot those, right? You dot those. I think it's doable, right? This is doable because you'd have just a bunch of powers of t and constants. It's not fun, but it's doable. There's a natural log in here. But I think that'll be okay because when the 2t hits it, I'll have a basic u sub there. This is all doable, right? But the fundamental theorem line integral was much, I think, more efficient than this. I'm going to stop here. We should get the same answer, though. Uh-oh. So here I say we have not seen yet what it takes to show that a vector field in three-dimensional space is conservative, right? With two-dimensional, there's a quick check, right? There's a quick check. I haven't shown you a quick check if I give you a field that's three-dimensional, right? We will have that. It's coming. For now, though, I'm going to tell you that this is conservative. I'm just going to tell you it is. And I want you to find the potential function. So this is very similar to what we were just doing, but now your scalar function is a function of 3 variables instead of 2 because your vector field is 3 components. All right? So if I tell you that this is conservative, right, if I'm telling you it is, then here's what you know. You know that that field is the gradient of some scalar function, which we know is the partial of f with respect to x, partial of little f with respect to y. Now the new thing, partial of little f with respect to z, right? We actually have 3 pieces. And we can start matching things up again, right? This has to be this. This has to be this. And this has to be that, right? I'll start with the very first thing. I know that the partial of f with respect to x must be 2xz plus y squared. You all agree? What now? Antiderivative with respect to x. Okay, let's do it. The antiderivative of the partial of f with respect to x, and then the antiderivative of 2xz plus y squared with respect to x. All right, left side is what? Just a little f, right? Just a little f. Equals. Okay. So we're doing the antiderivative with respect to x, which means we're treating the y and the z like they're constants. So what is the antiderivative of this? X squared z. And then plus antiderivative of that with respect to x. Xy squared, or you could say y squared x, right? Either way. Okay, now here's where we have a change. What can you tell me about the constant? It could have y's or z's. It could have both, right? So what I'm going to do here is put plus g of yz. It's some function of y and z. Potentially. It could not be, but I have to account for the fact that there could be y's and z's and only y's and z's, right? This means there's no x's, just y's and z's here. But I don't know what this is. And now, what? Take the derivative of that with respect to y. You could also do z, but I'm going to do y. Okay, so take this, take the derivative of this with respect to y, and just, I'll put this in red. This is where we are, right? If we can figure out what this is, we're done, right? Which means I just need to figure out what g is. But I can't yet. I don't know what g is. So I'm going to take the partial of f with respect to y. On here, what is it? Right here. Partial of this with respect to y. 2xy. Plus, so derivative of that 0, because there's no y's. Derivative of that, well, this 2 comes down, 2xy. And then what's the derivative of this with respect to y? G sub y, right? It's the partial of g with respect to y. That's what it is. I don't know what it is, but that's what it's supposed to be, right? We're differentiating, right? This could turn out to just be a constant. It could, but I have to treat it like it's not. Okay, now what? Important step. No. We compare it. I know, where did this come from? This came from, this all started from this idea, right? I said these two have to be the same. This has to be this, right? And from that, I deduced this, which I deduced this, which I deduced this. But I know something about this, don't I? I know that that has to be what? 2xy. So I know that 2xy plus the partial of g with respect to y must equal 2xy because of this. And cancel out your 2xy's on both sides, and you get the partial of g with respect to y must be 0. And now if you integrate both sides with respect to y, careful, let me do it. If I integrate both sides with respect to y, right? If I integrate both sides with respect to y, what's the left side? G, right? Whatever g is. What's the right side? It could have a z in it, right? It could have a z. So I don't want to use g again. I'm going to use h. I'm going to do h of z. This could be some function that just has z's in it. And then the derivative of that with respect to y would be 0 because I know there's not any x's. Yeah, that should, right? So what we've done at this point is we have said, look, remember over here where we were saying that f was equal to this plus some function that potentially had y's and z's in it? We now know that that g has to be a function of just z's, that it can't have any y's in it. Okay, any guess as to where to go from here? see, what partial what with respect to z? Let's go back to this, right? We know more about this now. We're going to replace this with h of z. And then we're going to take the partial of this with respect to z, and it better match with this. So we're going to play a matching game again. Should I run through this logic again, or are you all following it?
Yeah, we're good.
You're okay? All right, so I think I'll just pick up where I was right here. I'll erase. So I'm going to pick up where we're here. We know so far that the f we're looking for is x squared z plus xy squared plus some function g of yz. But now I know from this that that just must be some function h of z, a function that only has z's. And now I differentiate this with respect to z. And when I do that, I get x squared, 0, right, plus the derivative of this with respect to z. But what does this have to match? It has to match this, right? It has to match with that. So that means that the x squared plus partial of h with respect to z must be the x squared plus 3z squared that I have up here. And the x squareds cancel. The x squareds cancel, and I get partial of h with respect to z is 3z squared. And then we integrate both sides with respect to z. This is just h, right? And this side is z cubed plus some constant. There could be a constant there, right? I'll never be able to resolve that constant, all right? I'll never be able to, but that's okay because the potential function will be any function. You can plug any constant you want in there and it'll be a potential function. So I think I have a final answer, right? All I needed to know was this right here. I was trying to figure out what this is, and I needed to know what h of z is. Now I know what h of z is. It's this right here. So my final result is, I'm going to write it this way. My scalar function, right, the potential function, the generic potential function is x squared z plus x y squared plus z cubed plus some constant. There we go. That is the potential function. And guess what? The fundamental theorem of line integrals extends into this situation as well, right? So if you give me a curve, right, in three-dimensional space, this all works the same way. So you could just evaluate the two endpoints of the curve. We're done. We're done for the day. Let's call it. I think this is a good transition point. We're getting into 13.4. Green's theorem, it's going to be a nice theorem. So we're getting there. We're getting there. If you came in, didn't hear my announcement at the beginning of class, I'm going to give you 2 take-homes for Thanksgiving. No? No? Okay, no, that's not what I said. What I said is I'm not going to give you any more take-homes until after Thanksgiving. That way you can try and just take a breath, all right? Relax a little bit, focus on some other classes, do your homework, that sort of stuff. And then when we come back, I will send you the next exam. Now, if you're one of those people like, you know that next week you're going to have some free time, let's do it by request. If you want me to send you the next test, then send me an email, and I will get it for you, all right? What else? What do we have schedule-wise? Let's just look at our schedule. I know y'all want to go, but let's see, because it's coming fast, right? After Thanksgiving, everybody's like done, right? Your brain check, or has that already happened? Has that already happened? Have y'all checked out already? This is the wrong class, sorry. We wish, right? Maybe not. Series? I think we're okay on our schedule time-wise. So where are we supposed to be today?
Yeah, we just covered the November 20th.
November 20? Perfect. Perfect. This is great. This is great. Now, I know it's an extreme pace, all right? I know it's an extreme pace. But I promised this in the beginning of the class, right? I did say when we get to chapter 13, it's a lot of material. So Green's theorem will take me a full day. It will definitely take me a full day, right? Curl divergence will not be a full day, I don't think. This right here, this section right here, parametric surfaces in their areas, this takes me 2 days. And then surface integral, this is like 1 to 2 days. Stokes takes me a day. See, I'm trying to squeeze Stokes and divergence into 1 day. So the fact that we're a little ahead here is actually good. It's looking like we'll make it to the end. Yeah, we're in good shape. You know what? We have 6 minutes. Let me go ahead and cover Green's theorem. I'm kidding. Y'all go. Y'all go. Y'all have a good weekend already, right? Jeez, man, this keeps happening too fast.
Would it be possible for you to explain what the issue with our geometry was in that first example that we did?
Yeah, we can. Let me turn this off. Is it bothering you? Yeah. Yeah.